Electric fields. Welcome to the new unit. It's not anything too crazy, kind of a short unit, but there is a little bit more math in here, a little bit more involved. And some of these concepts are a little bit weird because when I say electric field, I'm not sure what some of you think, but it's something that you don't really see often, right? And you deal with electricity stuff every day. You have an idea of what that is, but when you hear the word electric field, you don't really know exactly where it's coming from. So we're going to start with just conceptual electric fields, doing some stuff with that. That's what this lesson is today. Then we'll look on actually doing some calculations with how strong electric fields are, and then we'll look at a famous experiment called the Millikan's oil drop using electric fields. So what, electric fields and electricity are kind of two different things, okay? Um, this unit is about electric charge, okay? This is not the same thing as electricity. They're related, of course, but they're not the same thing. Electricity is when you have moving electrons, okay? They're moving electrons usually through a wire or some type of conductor. You get a current that's measured in amps. When you flick a light bulb or a light switch and a light bulb turns on, that is electricity, okay? That is a grade 12 topic, okay? That is not what this is. Not what this is, okay? This is very different. This is electric charge, okay? This is essentially looking at individual protons, electrons, and or just general charged particles, okay? Yes, they could still be moving, right? We're going to see how accelerations can show up in this unit. But it's not a steady stream through a wire. We're looking at kind of individual charges that we're going to place around, and we're going to see what they do and how they interact with each other, okay? So electric charge is measured in coulombs. It's the SI unit. It was named after somebody with the name Coulomb who discovered it. And it has the symbol C, and usually we use charge as either like little q or big Q. That's the notation, the variable used for charge, okay? So before we jump in, let's look at some terminology, okay? Electric field, which we use a big E like that. Okay, that's our electric field. That is the region of space around a charge where a positive test charge experiences a force. Okay, this positive test charge is an important topic. Okay, it's an important idea to know because we are saying here's a test charge. This test charge is kind of like a super tiny spot in space where we're going to put this little tiny thing, and this thing has a positive charge, and we know exactly how much that charge is. Okay, but it doesn't do anything to the field around it. It just exists and it experiences a force. Okay, it's like when you go to ride a roller coaster, right? You are testing out that roller coaster by riding it. You are sitting in the roller coaster. You are definitely there and in the roller coaster, but you are not actually disrupting the path of the roller coaster, right? You are not heavy enough to disrupt what the motion of the roller coaster as it goes through. That's what a test charge is, okay? It's there, it's experiencing things, but it's not big enough to change anything around it, okay? So that is our positive test charge. That is different from what we call a point charge. A point charge is an idealized charged particle, because remember, physics live in this fantasy land where everything is perfect. It doesn't have a size or a mass, but the big thing is it creates an electric field around them. So we have that as our roller coaster, right? We put our roller coaster there. It is the most perfect roller coaster. It sits there, and that creates a field around it. And then we take our positive test charge, which is you riding the roller coaster, we put it inside the field, and we see what happens. Okay, so that's just some terminology that we're going to be throwing around in this unit quite a bit. And remember, this should be a review from before. Opposites attract, and like charges repel, right? That is our kind of the basic that you learned when it comes to electricity and stuff like that. Opposites attract and like charges repel. Okay, you take two positive charges, you put them together, they're going to repel. You take a positive and negative, they're going to go together, just like magnets do. Okay, so what we need to do is a way to visualize electric field lines, because obviously you've never seen an electric field line out in the real world. That's because you can't see them. Okay, so physicists decided, we need a way to visualize what's happening here. How can we visualize like what is happening to these charges and fields? And this is all this invisible stuff. Okay, and invisible stuff back in the day used to get you called a witch. And you don't want to be a witch, right? You want to be a physicist. But a lot of times physicists and witches went hand in hand because they're talking about a bunch of things that you can't see. So that's why they said, you know what, let's draw some electric field lines, help us visualize and represent what is happening here. Okay, they're representing lines of electric force created by anything that is charged, a charged object. Okay, the big thing, and I'm going to say this over and over again, is electric field lines represent the direction of force on a positive charge. Okay, I'm going to come back to that a little bit later. But what that means is that a positive charge, like a proton, for example, will follow the electric field lines. It will move in that field, right? Because remember, positives, like charges attract, or like charges repel, opposites attract. So there's going to be movement here, and they will follow the path of the electric field lines that we draw. Negative charges will do the opposite. So an electron will go in the opposite way. Okay, we'll come back to that a little bit later, but I wanted to say it again at the start just so it's in your head. So there's some very, very specific rules about how to draw electric field lines. They're honestly not that picky, but these are kind of just the guidelines of how we draw them. First thing is that they must contact the charge at 90 degrees. Okay, now that seems like it's super important, but if I give you a test charge, let's just say I wanted a circle. That's what I wanted. Okay, here's a circle. Let's say that is a positive charge, like so. If I'm going to draw an electric field line, okay, it can't come out like that. Okay, that right there is bad because that angle is not 90 degrees. That does not equal 90 degrees. But if we wanted a good one, we just have to go straight up like that, right? That is good. That is 90 degrees. Okay, that's all it's saying. Does it have to be perfect? No, not at all. I just want you to see, don't do this. Okay, don't do that. Stick with these straight out of the circle. Okay. They may be drawn in two dimensions. That's just kind of a self-explanatory. You're going to get things going up and down and left and right. That's kind of a moot point. All field lines must start from a positive charge and travel towards a negative. This right here is super, super important. Okay, you start positive and you end negative. Okay, I'm going to highlight that again. Start positive, go towards the negative. Okay, so you start positive, and you go towards the negative. Always, always, always. This is like your high school career, right? You start in grade 9, you're excited, you're ready to go, you're ready to tackle high school, and then by grade 12, you start to get like grade 10, grade 11, you start to get a little bit more cynical, a little bit more negative. By grade 12, you're kind of cynical. That's kind of what these things are. Now, that's not entirely true, that's a joke, but right, you're starting positive and then you're always traveling towards the negative. Okay, number 4 is also a super important. Field lines must not cross. You cannot cross. I watched a video once that said no crossy. Just a fun way of seeing it. They cannot cross. Okay, you cannot have two field lines going in opposite directions like that, because right at that middle point there, what the heck happens there? Okay, is the electron, which if we're going to put an electron or a proton there, is it going to follow the red line or is it going to follow the green line? It doesn't know. Okay, so they cannot cross, they do not touch. Okay, the other thing about this, which not super important, but we'll do a little bit with, is the number of lines leaving a positive charge is proportional to the magnitude of the charge. Okay, the number of lines is essentially proportional to the magnitude of the charge. Okay, which means the number of lines is proportional to the strength of the field. More lines, a stronger field. So you draw more lines, you have a stronger field. If you have a charge twice as strong as another one, you're going to have twice as many lines. That's it. There's not math here, it is just a visual representation, okay? Everything about electric field lines, everything that I just talked about, it's just a visualization tool, okay? You're not really going to get any rigorous math happening here. This is more to help visualize what's happening here. So let's draw a couple, okay? Let's draw a positive point charge, negative point charge. We'll separate them. They're not attached to each other. So kind of what this looks like, okay? We'll have our charge. We'll put a plus in the middle. That is our positive charge. Now, if we want to draw some field lines, remember this is positive, so we leave the field. Literally, this is all that's happening. We're just drawing some lines. It doesn't matter where the lines you draw. This right here is perfect. Okay, kind of ugly. There's 5. I don't like 5. We do 6. There we go. Okay, perfect. There we go. That is an electric field diagram. Okay, notice they're not perfect, right? But each one of these is kind of at 90 degrees. Okay, it's approximately 90 degrees. Okay, the only thing we're not doing is we're not tossing things out like that. Okay, that's bad. I'm just going to erase that so you pretend I didn't do that. Okay, there. That is a positive charge. They kind of go off into infinity, right? And if you notice, the lines over here, if I were to draw a circle like this, the lines here are a lot closer than the lines when they're out here, okay? That is because the further away you get from the charge, the weaker the field is. So the field out here is going to be weak compared to the field right next to the charge where the lines are closer together, okay? That's your strong field. Okay, that's just one of the nice visualization tools for this stuff. If we want to do a negative charge, well, you guessed it, toss a negative. If you want to write negative Q in there as a negative charge, that's totally cool too. Well, guess what? All these lines are just coming from infinity, and they're just going there. They're going towards this charge. Doesn't have to be anything pretty. I'm just doing random lines. There we go. It's fantastic. Okay. They're kind of coming out from this space out here where the field is weak, coming towards the charge. Remember, the path that a positive charge will follow. So if I were to put right here a proton, I'll say P plus, right? This proton, positive charge, is going to want to go towards a negative charge. So this thing is going to follow and move and accelerate towards the negative charge. That is what the definition of the electric field lines. If I wanted to go back to our positive charge and I did the same thing and I put a proton over here, well, positive charge, they don't like each other, which means this proton is going to move away. That's it. Okay? Cool. Let's maybe have more than one charge. Okay? This is called an electric dipole. Okay? Opposite sign, but equal in magnitude. So that means we're going to have one positive charge and one negative charge. And if we want to draw this, right, these lines are going to leave our positive charge, but then they're going to go towards the negative. And since there's a negative there, it says, hey, you know what, I like that. Okay, this one, it's going to come out like that, but it's going to be like, you know what, I feel something over here. I'm going to go over there. Same thing here. I'm going to go at 90 degrees, but it's like, oh, shoot, I feel something over here. I want to go there. And they just kind of loop around. They're kind of these loopy thingies that look like this. And notice how I'm going towards the surface at 90 degrees. I am not having lines that go out like this and in like this because that's no longer 90 degrees, okay? This is bad. It's not 90 degrees. We like 90 degrees or as close to it as possible. Obviously, right here, how I drew this, not super 90 degrees, but I tried. It's close, okay? This is a lot closer than that, okay? That's it. What's really cool about these things is even if you get the lines that come out on this side, like that, looks like they're kind of going off forever, but guess what? Eventually they loop around. You don't have to even draw these dotted because it's going to mess up your page. They loop around, and guess what? They come right back into the charge, okay? Equal in magnitude means here we have 1, 2, 3, 4, 5, 6, 7 lines. So we have, of course, 1, 2, 3, 4, 5, 6, 7. Same number of lines, equal in magnitude. Cool. Okay. 2-point charges with the same sign. Okay, this could be both positive, both negative, doesn't really matter. Positive, negative, like so. Oops, sorry, same sign, both positive. Okay, now we're going to get a field line that comes out like that. Okay, we're going to get a field line that comes out like that. But field lines can't cross, and positive charges don't like each other. If you are standing right here and you're trying to get away from this positive charge, you're going to go like that. But then if there's also a positive charge coming out of this way, you also want to get away from it. So what happens is they kind of go up and they're like, nah, nope. And they nope out of there. And they go like, nah, nope, I'm going to get out of there. And they just shoot away. Okay. Eventually, technically, there might be a negative charge over here in infinity, so it might kind of loop back, but that's something for another day. If there's nothing over there, just kind of loop away. Great. Same thing down here. They go, yeah, no, I'm good. And they go down, yeah, no, I'm good. Okay, and then really we can just fill in the lines, boom, nah, no. Because remember, these lines cannot cross. So no matter what we do, these things cannot cross. And what's nice is the ones on the back side, they just go out forever. Nobody cares about those ones. They just disappear. Okay? Now, something we're going to talk about in class. What happens here? Right in the middle. Okay? What happens? We don't know. Nobody knows. Let's talk about it in class. I want you to think about it. Okay? So those are two charged with the same sign. We can really have whatever orientation we can. The other thing I'm going to show you is parallel plates. Parallel plates is essentially just two long flat pieces of metal where one plate has a positive charge. So we might put some positives up here to say it's got a positive charge, and down here, negative charge. Put some negatives. Parallel plates, this unit loves them. Okay? And why they love them is because if we were to draw our free body diagram, sorry, electric field line, we're just going down like this, positive to negative, positive to negative. On the ends, we might get a little bit of curling around right on the tips, but most of the time we just get straight down. And the reason that this unit loves them, because inside here, where I'm highlighting, okay, this region inside is a perfect uniform electric field. Uniform electric field, okay? Which we can control, that we can control very easily based on what type of charge we put on the top plate and what type of charge we put on the bottom plate. We can control it really, really nicely, okay? So that is the electric field diagram for some parallel plates. Now, there's another one. I want you to try this. We've got point charge Q plus 3Q. Okay, you can do that looking at magnitude, number of lines. We'll go over that in class. And then there's this simulation I want you to play with a little bit where you get to do your own thing. Okay, then what the positive charge lines, we're going to talk about that more in class. This is more of an introduction on how you draw these things. I kind of showed you already what positive charges will do, like so, but we'll talk about the rest in class together.